Hey everyone, and welcome. Today we're jumping into a really fun puzzle. Now, on the surface it looks pretty straightforward, but it's got some surprisingly deep things to teach us. We are going to be solving the Park Paths puzzle. So here it is. This is our map from Arrowhead Provincial Park. Your challenge is super clear. Find the absolute shortest path from Station X all the way over on the left to Station Y on the right. Seems simple enough, doesn't it? But let's see if our gut feelings actually line up with the real answer. Okay, so to get started, the source material gives us a little head start. We're going to look at 3 different paths that a few hikers actually took. You can think of these as our first clues, the breadcrumbs we need to follow to crack this thing wide open. Now hold on. Before we start adding anything, take a close look at that map. See that? Some distances are in meters, but others are in kilometers. That's not going to work. To compare apples to apples, we have to get them all into the same unit. So we're going to use meters. That means that half-kilometer path becomes 500 meters, and that big 2-kilometer stretch, that turns into a whopping 2,000 meters. All right, let's follow our first hiker along Path A. They start at Station X and head to the rabbit marker. That's 500 meters. From Rabbit, they go to Deer, another 500 meters. And the final leg, from Deer to Station Y, is 1,000 meters. Add all that up, and you get a nice, clean 2,000 meters total. Easy enough? Now let's check out Path B. This hiker took a completely different route. From X to the Beaver marker is 750 meters. Then they hit that really long scenic route from Beaver all the way to Chipmunk. That's our 2,000-meter leg. And then a final 300 meters from Chipmunk to Y brings their grand total to 3,050 meters. Wow, yeah, that's quite a bit longer. Okay, and Path C is where things get really interesting. It just goes to show that a path that looks more complicated isn't always longer. This one really zigzags, from X to Rabbit, then to Moose, over to Raccoon, back to Deer, and then finally to Y. But look, when you add up all those little short sections, the total is only 1,950 meters, so it's actually shorter than Path A. So, let's answer that first question from our puzzle. Who walked the furthest? Well, this bar chart makes the answer impossible to miss. With a journey of over 3,000 meters, the hiker on Path B definitely got their steps in for the day. No contest. All right, so we've compared the paths people took. But that wasn't the real challenge, was it? The real challenge is finding the absolute shortest path. Now, you might be thinking there's a pretty obvious, common sense way to do this. But is the most obvious strategy always the best one? Let's find out. So, one strategy that seems really smart is something called a greedy algorithm. And the logic is super simple, which is why it's so tempting. Whenever you get to a fork in the road, an intersection, you just pick the shortest possible path right in front of you. You're being greedy for the smallest number. Makes sense, right? So let's try it. Let's put on our greedy hiking boots. We're at Station X. The shortest path is the 500-meter one to Rabbit. Okay, we take it. Now we're at Rabbit. What's our shortest option? The 100-meter trail to Moose. Done. For Moose, the shortest is 250 meters to Raccoon. You see the pattern here, right? We just keep picking the immediate, easiest win. But, and this is a huge but, here's the twist. If you follow that greedy strategy all the way to the end, you actually trace out Path C, which we already know is 1,950 meters long. And what's so fascinating is that even though that path is better than A and B, it's a trap. The source material says it perfectly. This strategy does not work in general. It's a classic case where a series of good short-term decisions does not lead to the best overall result. I mean, how wild is that? The simple, intuitive, common-sense approach totally fails us. So if we can't just pick the shortest step every single time, how in the world are we supposed to find the path that is guaranteed to be the shortest? Well, this is where we bring in the big guns. This is the part where we pull out the powerhouse tool designed for exactly this kind of problem. It is time to crack the code with the guaranteed method. The real solution is this brilliant strategy from higher mathematics called Dijkstra's algorithm. Yeah, it's a mouthful, I know, but instead of just looking one step ahead, it is so much smarter. It methodically explores and keeps track of the shortest path from the start to every single intersection, building its way outward until it nails down the absolute best route. It's systematic, it's powerful, and it is foolproof. So, after we let this powerful algorithm do its thing, it reveals the true optimal route. And it's a path we haven't even seen yet. It goes from station X to rabbit, then on to moose, then to raccoon, then it cuts over to chipmunk, and from there, it goes to station Y. And the total distance for this incredible path? Just 1,450 meters. That is way shorter than Path C, and it blows Paths A and B out of the water. That is our definitive answer. So that was a really fun puzzle, but why should we care? What's the big deal? Well, the logic we just used to solve this little park puzzle is actually the same logic that connects directly to the technology you use every single day.
I mean, it's a totally fair question, right? Why does a puzzle about some trails in a park actually matter in the real world? It might seem totally random, but believe me, the logic that we just walked through is secretly running our entire modern world.
Seriously, this exact type of problem, finding the shortest path, is the engine behind so much stuff we just take for granted. It's in your phone's GPS, calculating the fastest way to get to your destination. It's how data packets find the most efficient route across the internet in milliseconds. Airlines use it for flight planning to save fuel and time. It's the backbone of logistics and supply chains. And it's even how characters in video games figure out how to navigate around obstacles. And that really brings us to our final thought here. This shortest path problem isn't just about maps and distances. It's a whole way of thinking about efficiency and optimization. So the question I want to leave you with is this. What other shortest path problems are hiding in plain sight, all around you, in your everyday life?